audio check and then we'll start.
Test.
I'm not going to put that far. That could be streamed in. So just be sure to, for the benefit of this, be sure to introduce yourself and what you're talking about, even though you did it in the other room.
Yeah. Oh yeah, I gotta plug my company. Come on.
Yeah, definitely. You ready?
Yeah, sure.
Okay, let's start in 10.
So close.
Yeah. Okay, you're good.
I need to stand back here.
You're fine. Go ahead.
All right. Welcome, everybody. My name is Ben Pomerenke. I'm a software developer at Worldwide Technology. I've been doing software development for around 12 years. AWS sparked my interest a while ago, but it wasn't until 2 years ago that I actually got to start doing it. I've gotten to work for 2 customers working at AWS now. And I thought it would be cool to show you kind of a mock example of an architecture. So today we're going to be talking about Message Buddy. This is not a real app. In fact, it's actually kind of a horrible app. But it shows off some core technologies in AWS. I recently came off of a customer engagement that had a very similar architecture. It's not one-to-one. So this is a realistic... I'm losing it.
What happened?
I guess I got to keep my screensaver on.
Yes, please.
So the architecture we're going to be going over today is a realistic architecture. It's very similar to something that a customer just paid over $1 million for. So I didn't create the entire architecture because I spent about 40 hours, not 9 months, which is what they paid for. And it doesn't have the same level of polish. So to kind of talk about the different technologies, the thing I wanted to highlight in this presentation is IoT Core. It's a really cool service that Amazon provides to do IoT things. I used to tinker with IoT devices. I don't do it as much anymore. So instead of IoT devices, I have iPhones, but they are meant for sending the IoT Core messages. I'm also going to talk about Lambda. So there's 3 instances of Lambda in this application. So we kind of use Lambda to glue everything together. So we have Lambda coming in from the message broker from IoT Core, going into Dynamo. We have Lambda that is feeding off of the events that Dynamo is generating, and we have Lambda that is accessing Dynamo to feed up data to a RESTful API. And then to get the data out to the rest of the world, we have it behind a API gateway, which is just a REST API gateway as well as a WebSocket API gateway. And then we're using S3 to actually host the web content. So I also have a web app that I'll be showing you in a little bit that is written in Angular. So I'm not going to spend a ton of time talking about iOS and Angular, but I just want to call out that they are in the data stream, but we'll be focusing most of the attention on AWS services. So before I do an example of the app, I want to jump through some of these services. So the first one being IoT Core. So IoT Core is basically a bunch of helper utilities that are built around MQTT. So MQTT is a messaging protocol. It's meant for low latency messaging. So it has some protocols that allow it to ensure that messages get delivered. So it's really good for message passing between devices, especially if you're sending small amounts of data frequently, and you don't want to lose that data. In IoT Core, you can actually establish these things called rules, and rules can be anywhere from a DynamoDB rule that just dumps data from the message into Dynamo, to more complex Lambda functions where you can actually process the data and do something with it. You can also use things like SQS and SNS to actually trigger other things. So SQS is a simple queuing service. It's a more persistent layer than IoT Core, and it also has, you can also do some things like if it fails to process the message, you can do different things with it. And SNS is a way to send notifications to other applications. So, before I go to the next part, I just want to show you guys kind of the general interface inside of AWS. And it's in the same browser, that's why. Okay. So right now I'm accessing AWS through a single sign-on that I get, it's a sandbox that I have as part of my work. So normally this isn't how you would log in. But I'm just going to jump over to the management console. Give it a second. All right, so who here has actually used AWS and seen the management console? Is this familiar looking? Okay, cool. I'll try not to move around too quickly in here, but for those of you that have never seen it. But I'm going to jump into IoT Core. And I apologize for the slowness. I guess my Wi-Fi is not the best. So this is the basic dashboard, and it kind of shows you some high-level stats about things going on in the ecosystem. If I jump over here, you can see I have 4 IoT devices registered. They're called test 1, 2, 3, and 4. This is actually test 2 and test 3, are the phones. Test 4 is actually my laptop. You can also see that there is some security layers here. So the way IoT Core works is to actually establish a connection to the broker, you have to have a certificate. That certificate is signed by AWS and is given back to you. And so when you actually connect, you pass in the AWS root certificate, you pass in your private key and your public key. Those are the things you need to actually connect. And that's how it establishes your identity. And then any messages you send during that session are associated with your thing. Okay? So as part of this, you can do some cool security things like if a device is stolen or lost, you can deactivate the cert. They can no longer connect to the broker. This was actually one of the reasons we chose this for our customer. They work in an industry that is all about security. They needed an easy way to know how to manage their actual devices that were out in the field. And this gives them kind of a one-stop shop. Okay, there's some other cool things you can do while you're in here. The thing that we use a lot to help us develop is the test. And so in here, there's like a web version of an MQTT client. So you can type in an actual topic name. In this case, I'm just going to subscribe to the topic the app talks to. And I believe it's connected. And then in the app, this is actually going to be sending to that topic.
Can you zoom in a little on the web?
Can. Give me a second. It's not the best interface. Okay, and you can see the message actually come over in real time. Okay, so this is a good debugging utility for when you're first wiring this up. Another cool thing is all of these topic messages are actually going to be logged. So you can send those logs to CloudWatch. So open that in another tab. And so you can debug things like, was the client able to connect? Was there an authentication issue on trying to connect? Or things like that. So just jump over here. Now these are IoT logs, so they can get a little bit overwhelming, but you can see here that this IoT client connected successfully. Okay. So this is also very helpful for debugging the initial connection state. Okay, some other stats about IoT Core. Let's pop this back open. So it can have up to, I believe, 50,000 devices connected to it at one time. So that means you can have 50,000 devices per account. Like all things in AWS, that is probably expandable. You just have to add that extra service ticket that says, hey, I want to pay more money. They pretty much will let you do anything you want if you ask them to. But the default is 500,000. Each client can only subscribe to 50 different topics. Once again, that's a default. You can get it bumped up. They can actually publish 100 events per second. So they can listen to way more than that. But they can generate up to 100 messages per second. And the price per million messages is $1. So let's say you have 500,000 out there. They tweet out a message in the morning and in the afternoon to collect some data about something in your factory. It'll cost you $1 for that day. Okay, so not very expensive. It's pretty cheap way of collecting a lot of data. Okay, I talked about the security already and the SSL certs, which is really nice because it makes it so that people can't listen in on your chatter, can't subscribe to your topics unless they're allowed to. But you can also tie the things that the rules are able to do to IAM permissions. So if you want to allow a rule to write only certain Dynamo tables in your account, you can actually do that. And you can segment permissions to allow for different rules to be able to have access to different resources, which is really cool. Okay, like I said before, it's all built on top of MQTT protocol, which means that the clients do not have to be anything specific. There is a library for MQTT in almost every language. The one I'm showing off today is in iOS. There's JavaScript versions of it, as well as just command line utilities. So it's relatively easy to get going from a client development perspective. So before I move on, is there any questions about IoT Core? Yeah.
Well, when you're talking about messaging limits, I'm assuming if you're sending messages out to a client, that's a message in your 500,000 or your million per dollar. Does the client send a message back that counts towards that, or is that sort of out? Is there bidirectional at all? How does?
So that's talking specifically about the actual message. There are acknowledgments. So depending on what you set the QoS. So the way the MQTT works is there's 3 quality of services. 0 is a best effort. It's kind of like UDP. Think like how UDP works. It just sends it out and hopes somebody got it.
Right.
There's also QoS 1, which is probably the most common, which you actually get an event. So the client actually gets some kind of acknowledgement that the message was successfully received by the broker.
Okay.
And then there's QoS 2, which means only one person's going to get it. Once they get it, it like basically ensures somebody's going to get it.
But those acknowledgments would be included in the messages. That's not.
No, those are not part of the actual message. That's actually part of how MQTT works.
Okay.
And so it's the broker that's actually doing those acknowledgments. It's not actually the other clients.
So if you notify 1 million people or 1 million devices and you receive 1 million acknowledgments, that doesn't necessarily mean that you're paying for 2 million messages.
Correct.
Got
Yep.
it. Cool.
Any other questions? I think the message payload size. I thought I was going to put I thought I put this on here, but I think the message payload size has a max of like 128K. It's relatively big. We were actually sending graph data across it and had no issues. We ended up compressing it on one side anyways because there was like 10,000 data points, but we had a lot of extra room in the payload. So it's pretty cool. You can send a decent amount of information across the wire. All right, so the next technology I'm going to talk about is Lambda. Hopefully you guys are familiar with this, but Lambda is effectively functions as a service. So you get to register some code in some database somewhere, and when you say I want to run that code or something else says I want to run that code, it loads it into memory, executes it. It usually leaves it in memory in some fashion for some amount of time. They will never publish how long that is, but we think it's around, it's anywhere from like 1 to 4 hours. It'll be what we call hot, which means it doesn't have to load it into memory. And those functions can execute all over the world. So we're talking about cloud. Like this is like kind of the essence of what cloud is. This code is, you have no idea where it's running. You have no idea how many computers are backing it up, but it's out there somewhere and it's executing the code. There's equivalents in most cloud providers. I think in Google they call them functions. I don't know what the Azure equivalent is. But these are kind of the coolest, we use them a lot to glue our stuff together, to add some logic in between services. And so that's really where they shine the most. They can be a little slow or unpredictable, so you don't necessarily want to use them for things that are like high availability. Like if you need to like ensure a response time for something, like maybe you need a web request to be less than 30 milliseconds or something like that, you may not want to lean on something like a Lambda, because you can't actually guarantee how quickly they spin up and execute their code. I will say they are super fast, and you can control how much memory you give them to make them faster. So in this code, we actually did, we're using C# or .NET Core, and that is actually one of the fastest runtime languages. So once it's spun up, it executes the fastest. However, it is one of the slowest cold start technologies. So we've actually seen if you put the memory at like 256, it can take up to like 4 to 6 seconds to actually spin up the Lambda. And then once it's hot, it's super fast. So we actually bumped up that. I think we went to 2048 megabytes, and we got it to reduce by a factor of 10. So the actual cold start on our Lambdas is somewhere between 200 and 500 milliseconds. So the way we were actually using to deploy this code, so the code base I have here uses Terraform to do the deployment. It's actually not the intended purpose of Terraform, but you can use it that way. Some of the most popular ways to do it is a technology called serverless, AWS serverless. It's kind of a strategy for building Lambdas and deploying them, but we were unable to do that. So just to show you a little bit of the code, so I'm going to jump between a few different platforms here. So I'm using Writer as the C# editor, and then using Visual Studio Code as the Terraform editor. So in here, it's basically a function call, and usually when you design like web services or applications, you'll kind of have one like main entry point of the whole application, and then everything else will spin off from there. It kind of works the same way. This function has 3 entry points actually, because I have 3 Lambdas in here. But the idea is that the project is just this one Lambda source code. Okay, and then you can use methods within the Lambda source code for a variety of reasons. So we generally group our Lambda code by domain, even though we may have 5 Lambdas that interact. So this is the messages project. So there's 3 Lambdas in here that actually deal with messages. There's the one for getting all the messages, so that's used in the web app. There's the one for posting a new message that's also used in the web app. And there's one for notifying a message update, which is the Dynamo event that I'll be talking about in a second. So all 3 of these Lambdas are actually in the same project, and that same project gets put out there in AWS world for what to load, but then when it actually executes, you get to specify which function you actually call. Okay. And so one other thing I get going on here, and this is something that is very helpful, especially if you have a lot of common code that you want to share among Lambdas, we've implemented dependency injection. So here, how many of you guys are familiar with dependency injection? Show of hands. Okay. So when we actually started 9 months ago, we were a little worried that dependency injection might slow down the spin-up costs. Turns out it had nothing to do with it. And so we went for a very long time with what we call poor man's DI. It was really painful, but about a month or 2 before the end of the project, we discovered just the .NET Core dependency injection framework, and you can see it makes it kind of one place to understand what all the things this Lambda may use. So you register all your dependencies here. A few of these dependencies actually require some configuration. So for instance, DynamoDB requires that you set up some mapping between object types and table names, and so we do that in there. API Gateway requires that you give it which API gateway you're interacting with, so on and so forth. So we've extracted those out into some simple just configuration methods that will go to the Lambda, figure out an environment variable, and then create a SDK wrapper that you can use later. Okay. Some things need a little bit more help. So one of the cool things we found was DynamoDB context. It's kind of like an ORM. It's a .NET Core helper library that acts pretty much like an ORM. It's pretty lightweight. You don't actually have to do a ton of wiring up. But when you actually initialize it, you do have to connect types to table names. So in this case, and sorry, I'll blow that up. In this case, we have two tables that this code cares about, and we're going to wire those up with some type mappings. Okay. And then because we have dependency injection, it allows us to kind of organize our code in a good way. So we've abstracted all the actual work that the Lambdas are doing into this helper class called Lambda service. And then if you jump in it, you can see the specific things. So those of you less familiar with DI, this is pretty common to see some boilerplate code. What this does is allows us to inject these things from the service provider. And so what that's effectively doing is it's making available all the things we've set up and registered to this code under test. And so then the thing you're actually executing gets really small and succinct. Okay, another thing to call out, it makes unit testing very easy. So we actually have tests that go along with all these Lambda functions. And I think they still pass. Might have broken them at the end. And so if you are a fan of test-driven development, very, very easy to get going on that. Okay, and to just show you kind of an example of things you might want to do. So in this case, I have a get and a post. So the get's relatively easy. Comes in here, and it will scan the Dynamo table. Not the best thing to do, but that's what I did for simplicity. So it'll grab all the records out of the Dynamo table. It knows the Dynamo table because of the type mappings I was showing you earlier. And in this case, it's just grabbing everything. And then I've written this little helper method that actually will serialize the result into an API response. Okay, so you can see I'm using camel case resolver so that for the API's sake, it's all camel case. If you guys have ever used Web API, this should look pretty familiar. Most of the time, Microsoft defaults to Pascal case with its JSON, but JSON.NET, or I think it's JSON.NET, gives you this helper method that lets you say, turn it into camel case. So this has been relevant for most of my career in .NET because I generally work with either web apps, which almost always go camel case, or iOS apps, which always go camel case as well. Okay. So one other thing that's nice about dependency injection, it makes it really easy to share common code across the different pieces. And then there was one other thing I want to show inside this Lambda service. So there's also ways to, so this is the Dynamo example, but you can also use these other SDKs. In this case, I'm using the Amazon IoT SDK to publish a message. Okay. So basically every Amazon service comes with an SDK package. I believe .NET has 100% coverage. JavaScript is probably the easiest one to get going quickly, and so we use that in Lambdas as well. But I think also Java and Python are super big. So basically, anytime you want to interact with Amazon, there's almost always a helper library out there for you, which is really nice. So, and our Lambdas actually use those helper libraries when they do their work. Okay. Any questions about the Lambdas before I move on? Yeah. So it depends. So a Lambda is a single instance of a function executing. And so if you start one up and then something else needs to start one up in the same Lambda, it'll actually have two instances. Or if you start one up and then nobody's using it, and then you come and call the same one within a certain amount of time, it'll already be there. So it kind of depends on how it gets used. But for the most part, it spins up, does its work, and it stays there for 2 to 4 hours. And then the second time you call it, doesn't take the startup time, or the 100th time you call it. If you keep calling it endlessly, it'll stay warm the whole time. One thing to keep in mind, you want to try to avoid long running Lambdas. So generally, you get to specify a timeout when you actually create one. I think the default is like 90 seconds, but you want to be really careful not to do really long timeout operations, and that's because if something is pinging it, you'll spin up a new instance every single time, and so you can actually get into some blocking. So Lambda does allow you to have up to 1,000 concurrent executors. I don't think I've ever actually hit that limit, and I've worked in systems that have a lot of simultaneous Lambda executions. So like, I think it's just important that you try to avoid the really long running Lambdas. I think the code that I was just showing you takes 30 milliseconds, super fast. Man, Google Slides is not a good thing for transitions. Let me do this. Pull this guy out. All right. Oh, I can leave it open. Yeah.
So you talked about how you put all your message. Can I ask a question?
Yeah.
You put all your.
No, I'm doing so much right now.
Yeah, you gotta know what else to do. You put all your messages stuff together. Is there a reason? So if you're worried about the startup time and all that, why wouldn't you just put it all in one single instance instead of separating them out like that?
So you can do that. I mean, it's a code organization thing. The bulk of what your package, so like when you build a Lambdas, you compile them to DLLs just like you would anything. And they zip up with all the with all the helper libraries. The bulk of the size is actually not your code. It's actually a lot of the SDK stuff. And so really it's not going to be meaningfully different if you put it all in one place. But it is nice to only have code that needs to be here. Like for instance, the messaging thing uses IoT, Dynamo, and I think DynamoDB event streams. But like it doesn't use it. You wouldn't want to put that next to the code that say only does IoT Core.
Because it doesn't need all that extra junk.
Yeah.
Okay.
So yeah, and honestly, I don't think I got the right necessary don't know what the right way to organize it is. But logically for us, it was easier to think about the domain model, and that's how we organized it. But yeah, you can throw it all in one. Just becomes a very monolithic code base, and you don't need to do that. Lambda's super cheap, so I don't even know how to say what that number is per request. But like basically, unless you do infinite like recursive Lambdas, you almost never see the cost from Lambda matter. So I will say though, it is possible to have a Lambda call another Lambda that then calls the other Lambda. And you can get in those loops. I think one of our teams did it a couple years ago. It's kind of like a fun story to talk about. And they ran up, I want to say it was like $2,000 in a day, just on concurrent Lambda executions. So you got to be a little bit careful about calling other Lambdas from a Lambda, but you can do some cool stuff though. I think I talked through all that stuff. I think the coolest thing about Lambda is it supports all these languages. I don't know if you guys can read that, but we got Node, Python, Java, Go, Ruby, and C#. So it makes it very, very compelling to use as your platform if you have people in different technologies. So there's also things that are easier to do in some of these platforms. So like our application had a Lambda that would generate certificates for us because we self-sign the certificates. We actually wrote that in Python because we knew how to do that in Python. We didn't know how to do that in C#. Something about Microsoft does certs weird or something like that. So, so that was kind of cool. So like one person on our team knew Python really well. He wasn't a developer. He was one of our infrastructure engineers, and he actually wrote that on his own in Python, and then we put it next to all the other code that the rest of the team built. So you can also mix and match languages to allow multiple people to interact on the same project. The next one is DynamoDB. So DynamoDB is the managed database service that AWS gives. It's, in my opinion, one of the easier ones to work with. It's just kind of there, and it's really easy to get going. It is, I think it's a key value database. It's not a document database. But when you look at it, it looks a lot like Mongo, or if you guys ever use like Lucene, or something that it doesn't matter what the fields are, you end up searching the data in weird ways anyways. But it is really nice for JSON data. So every record is a JSON entry. You do only have to specify two things. You have to specify, well, the first one you have to specify a hash key. The second one's a range key. So the hash key is kind of the unique identifier for the data. It's actually how they segment the data across the internet. So, you know, everything with the same hash key is very likely going to be in the same physical server. But within a database, the data could be anywhere. So, they figure out how to separate it based on the hash key. The range key is optional. However, most of the time we use it, which allows you to have multiple entries per hash key. So things like, in this case, I think the hash keys I chose were the client ID, so the device is the hash key, and then the range key is the timestamp. So you can find all the messages by device if you wanted to. You can also specify secondary indexes. They're basically just easier ways to search the data. I will be honest, I never got there on our project. I don't think it's hard. We never needed it. It's crazy how fast Dynamo will respond. You know, it's built for finding sparse amounts of data out of a giant data set, and that's where the hash key and the range key come in. And so we had a DynamoDB that had millions of records, and it was like it was the same cost to look something up with millions of records as it was to look up one record. So it's super fast. You know, 10 to 15 milliseconds at worst, I think, is the worst we saw. It's very responsive to your needs. One of the cool things, too, is you can actually tie into an event stream that tells you everything that happens on that table. It's actually, in this app, it's how I notify the WebSocket to send, or that's how I notify the web app to know that there's new messages. And so you can check for, or you can pay attention to things like only new records. You can look for updates to records. You can compare the old value to the new value, things like that. So to actually utilize that event stream, you do have to use something like Lambda or SQS or SNS to actually do something with the data. But you basically just have to flip a switch and you have like an event stream to do whatever you want with. The max row size in Dynamo is 400 kilobytes, so decent amount of data for a database row. You wouldn't want to use Dynamo to store binary files. You could very easily max out that if you were storing large files. But you would probably want to store something like the metadata in a Dynamo table. You only by default get 256 tables. We actually maxed this out on ours because we were doing a table. We were doing 7 or 8 tables per customer. And so it was basically growing the number of tables pretty rapidly. But once again, like all things, you can have that bumped up. The on-demand price per million is 25 cents. So I didn't pull in the provision capacity. So you can actually choose how you pay for Dynamo. You can pay on demand, which means it will let you use as much as you want, but every time you use it, it's more expensive. Or you can do provision, where you say, I'm going to use 125 units of read every, I think it's every second, or maybe it's every 5 seconds. I can't remember how they do it. And you will pay for that at a much lower cost, but you are always paying for it because you can't change it dynamically. So when you're doing prototyping or systems where you have infrequent messages or infrequent reads and writes, I would always suggest the on-demand. We're using it for a system that we expect to be used 24/7 all over the world with 300 clients. So we actually calculated it's not going to be super expensive to have it on demand, and that way if there's ever a total boost in how many there are, we don't have to do some engineering to make it go up higher. Or if there's a drop in use, they're not having to pay for it. So that's kind of cool. It'll automatically bump up or down how much you want. So, if you guys have ever seen, let's see if I can get back to the screen with the web browser. The actual interface for it. So here's tables. So I have 4 in this account. Pop that up a little bit. And this messages table is actually the data that's backing the app. And so you can see I have a very, very simple schema with the hash key of a client ID, the range key of a timestamp, and then message text, message time, message type, and sender. The cool thing about this too is you don't actually have to enforce a schema. So for instance, if you have one client that wants to start randomly adding another field, say version, they can just start saving data. It's got to be valid JSON though. And the UI will just magically grow the columns it displays. The reason that works is this isn't actually stored in columns. These are actually just key value pairs. But this UI actually will render it best it can based on the data it finds. Okay. So this is really good for prototyping as well. I don't know if you guys have ever built a project where you have to do the data model and actually come up with the schema, and then you're wrong about it, so you got to migrate the schema, so on and so forth. You iterate. You spend a lot of time building these tools around it. Well, with Dynamo, you can basically build the entire app without ever defining a schema, and then if you want to afterwards, you can go back and replace Dynamo with, say, like an RDBMS, a relational database, or something like Mongo that is more managed. That maybe has a little bit more structure to it. So that was one of the cool things with ours. So if you guys didn't know this already, at Worldwide Technology, we try to work in an agile fashion. It doesn't mean we don't design or plan, but we try to do it in a way that doesn't waste as much time up front, so that we can actually get product out there and actually have people use it and tell us what they think, which actually drastically changes what you end up building. And so things like this are awesome for us because we don't want to spend the first 2 weeks just drawing an ERD. We want to spend the first 2 weeks building an actual piece of software that somebody will actually use, and then tell us we're completely wrong. That way we don't waste 2 months building the wrong thing. Okay. Any questions about Dynamo?
Are the transaction costs based on the reading or writing a single row effectively?
No, it's based on how much data you read or write. So rows are maximum 400 kilobytes, but in reality they're much smaller than that. So this row is probably, maybe a kilobyte, probably not even that. And so the read units are 4 kilobyte, I believe, chunks. So if you have a row that has all 400 kilobytes and you read that one row, that's actually 100 read units. And so in general, when you store data in Dynamo, you don't generally hit that maximum size. But you can do things, you can organize your data to limit how much you have to read. So for instance, if you have a secondary index, maybe you have this row that has 15 fields in it for, say, a piece of data, and you only ever want to look it up by timestamp. You can index the timestamp and do that query to find what row it is, and then you don't have to read all the data to search for it. Things like, I said earlier that scans are really bad. So scans will basically read the entire table worth of data, and I will cost myself all those reads just to find a single row. So you can get really expensive really quickly. I say that, and it's still stupid cheap. But you have to be doing some really bad things to cost a lot of money. I think our total bill for our project across all of our environments for Dynamo was like $10 a month. We had 7 environments with 600 Dynamo tables, and probably, we had automated tests going on, adding and removing data frequently, and it still didn't cost very much. So you got to get into like the millions of transactions for it to start mattering. So, which I did work on a project that did that, and our average Dynamo cost there was about $100 a month. So. Yeah, so the thing about if you're used to a relational database, if you go to something that's non-relational, the thing you got to think about is organizing the data in the way you want to query it, not structuring it so that you can query it with things like indexes or sorts or things that you normally do in query languages. You don't have those at your disposal. So you actually really have to think about how you pipe the data in. Things like event streams really help with that. So you can pipe the data in the raw form one place. You can stream out individual fields to another Dynamo table or to another index, and you can do all these things, all this data gymnastics while the data is coming in, so that it's ready to be queried in a really good way. So it's not completely abnormal. So like we were building something that had 5 different data streams for like basically one event. And so the 5 data streams would come in separately, and the one event would show up in the web browser. And so we actually considered building effectively the web data model as the data came in. We didn't go there because we could get Dynamo to go fast enough without doing that. But that's like a totally normal thing to do, which is to basically build your presentation layer of data while it's coming in, rather than what most classic applications do is they'll fetch the data out of the database all at once. Okay. Let's see if I can jump back. All right, and then most of this, if not all of it, is behind what is called API Gateway. So API Gateway is kind of the interface that all of your AWS services can use to get out to the web. So think, server URL. In AWS, you can build that up in API Gateway. And what that allows you to do is reuse pieces of the tree to spin off other things and reuse them. So I think usually when you register URLs, you think about like the path as one registration. So let's say it's messages / ID / authors or whatever, senders. In classic server architecture, you will register that route once. But in API Gateway, you actually build all the pieces separately. So you'll have one piece that is just the messages. You'll have one piece that's just the ID, one piece that's just the senders. And what that allows you to do is actually tie in integrations at each layer separately. But really, when you look at it, it's pretty much a API graph. It actually, the actual interface inside of AWS is actually, I think, Swagger backed. So if you've ever used Swagger, I think it uses the Swagger documentation to actually build itself. And so in this API, you can actually kind of see a top-level view inside of API Gateway of all the pieces that came together. And call out that each of these little expansion pieces is all its own AWS resource. Okay, so you can see I have my API with messages version. One cool thing about API Gateway is you can use it to actually test your API. It's got a built-in test utility. So this endpoint just gives me back the version of the app. So I'm on version 0.3. You can do things, it has built-in placeholders for things like headers and query strings. But this is a really good tool to actually debug like your Lambdas or your servers that actually you wire into API Gateway. The reason you'd use something like API Gateway instead of just like a Route 53 record to a server is that API Gateway can scale across the regions. It can optimize things. It basically can give one definition of how to get to your stuff and use that across the board. You don't have to set up things like load balancers just to get to your applications. It also has this concept of staged deployments. So in most cases where I've done this, I've never actually leveraged this technology, but if you've ever done like A/B deployments where you have one instance of your API that is the old version and you have the new one out there, you can actually deploy both of them simultaneously. An API gateway will not, it'll still look at the old one until you tell it to. And so you can do things like canary deploys with that, where you basically give a quarter of your users the new API version to make sure there's no issues with it. And then you grow it by 10%, grow it by 10% until you have everybody using the newest version of the API. So once again, I know all that stuff's possible. I've never actually done it. I do know that when you actually deploy it, it comes over here into this deployed state. And you can see these are actually publicly accessible URLs, okay, which you could put behind human readable name if you wanted to. So one thing that would be cool with this too, so like for our development, we have a lot of automated tests. So if you wanted to do to vet a new change, you could run automated tests against it before you make it public, and then you just flip the switch to make it public to everybody else. Once again, still haven't done that yet. Hoping to do it someday soon. You can actually have two different kinds of APIs. So this one's just a RESTful API, but I also have a WebSocket API up here, where you can define what happens when clients connect or disconnect. And so in this case, I've just wired those up to a WebSocket connect Lambda. And so this time, everybody, when somebody connects this WebSocket, it'll actually fire this WebSocket connect Lambda. So if I want to track how many connections I have, I can save that away. In this example, I actually save that in Dynamo. If I want to notify any of the active connections, I know who all is available to notify. So you can query that kind of stuff. And just to jump over really quickly, show some of that notification code. So when you actually go to notify somebody, you just need to know their connection ID. So in this case, I said I was saving it in Dynamo. So I go out and I query all of the, where is it? So I query all the active connections up here. And then I just iterate over them and call the management gateway, the gateway management API to post a new message to them. So that's actually writing to the socket based on who's connected. Okay. There are some limits around API gateway. Things like you can only have 10,000 requests per second for a specific gateway. You can only have 600 regional APIs, so those are APIs that are specific to a region. I think you can have like 150 edge optimized APIs, so those are things that basically you'll hit a server that's closest to you when you make a call to it. You can have up to 500 WebSocket connections per second, so you can have a decent number of clients actually making WebSocket connections. And the packet size for each message you send across the WebSocket is 128K. Okay, almost through the actual explanation of what is built, and I'll show you guys the demonstration in a second. The last actual AWS service is S3. So very minimal use of S3 in this case. Not to say that you couldn't use it more, but I'm actually using S3 to actually do the web hosting. So S3 is really nice. So basically it's just a giant file system. And there's some switches you can turn on that will actually turn an S3 bucket into a website hosted. So since the website in this demo is Angular, it's built as a single page app. It's just static content that can be loaded from anywhere. So it's actually in S3. One of the cool things that you'd normally do, which isn't in this demo, you would back a content distribution network with that S3 bucket so that the static content could be as quick to load all around the world as possible. With CDNs, you can actually specify how spread out you want the data. So the cheapest option is, I think, North America and Europe. I think North America and Europe's the cheaper option. And then there's the non-standard, or sorry, no, it's North America I think is the cheapest, and then North America and Europe's the next, and then the next one is like basically everywhere else AWS has a data center. So that way you can actually get people don't have to make 10 hops to get to your web server. It'll actually distribute that content across the web. So S3 is also where you would maybe want to store things that are too big for Dynamo. So we use it a lot to store a lot of our binary content. So things like reports or file attachments or things that the user adds to the system that aren't necessarily static but need to be, written to and saved away in a very protected place. One of the cool things about S3 is it's very reliable. Almost reliable enough that you may not even need to implement a backup strategy of S3. We do generally implement backup strategies, but more just for a CYA because we're not the ones that have to deal with the ramifications of losing the data. But in general, it's very reliable. You can actually you can turn on a few switches with a service called Glacier, which can take it out of S3 and actually make it more long-term storage. And so you could also archive data very easily if you wanted to, instead of just backing it up. One of the things we did in our actual application that's not in here is we actually would store any message that came through the brokers in S3 in raw form, so that if we ever needed to, we could replay it back. If there was ever like an outage or a loss of the production data, you could actually replay the commit or replay the messages as if they were happening. So we use it for a lot of backup and restore procedures in our operations. S3 is super cheap. It's 23 cents per gigabyte. So a lot of times people will use this to collect a ton of operational data, form what some people will call like a data lake that you can do like AI type stuff against. And like I said, it's very reliable. It's kind of expensive to actually be uploading data to it. So to add more content to S3 will cost. It's about half a cent per 1,000 items that you actually upload. But it's super cheap to pull the data out. So that's why you don't want to use it as like a makeshift database. But if you do want things you just want to be stored, they can just sit out there. And it's relatively cheap. Okay, if you didn't know, S3 stands for Simple Storage Service. But I don't know if anybody calls it that when working with it. The last thing I wanted to talk about is the way I glued all this together. So I learned Terraform 2 years ago, and I think I've never thought about using another tool since. So if you guys have ever heard of infrastructure as code, there's a lot of tools out there to do this. Basically, stop you from having to run scripts. You can write a script and then run a tool, and it'll apply the script. So Terraform is one of those. The cool thing about Terraform is it is one language style, but it has multiple providers. So all the Terraform code that I wrote is all for AWS, but you could easily use the same mechanisms to do the Google equivalent or the Azure equivalent. There's providers for all the different services out there. The code actually kind of looks like a modified JavaScript. So for instance, this is some Terraform code. And so I'll just go to the resource. So this resource right here is an IAM role policy. You give it a name, so that's the internal name, so Terraform knows what it is. And then you get to specify all the different properties. The properties are actually documented relatively well in the Terraform documentation. Come on, open up. And so I have a little plugin in Visual Studio Code that actually lets me click to the documentation if I want to see it. But basically, all of these key and values tell you what you're supposed to put there. The cool thing too is you can actually reference other resources inside of your Terraform. So in this case, I have a module up here for the Lambda that has some properties, and once that is out there in AWS, it can actually reference some of the actual resolved values for it. So in this case, I'm looking for the function name and the Lambda role. Things that are more dynamic would be things like the E tag, or I think there's a few ARNs in here as well, where it actually has to look up the actual ARN. But this is nice, so you can basically stitch together all these resources if they have dependencies on each other. You do it in code once, and then you say Terraform apply, and it'll actually go out there and see what's out there and see what it needs to build in place. So just yeah. So talk about some of the things we've already seen. The Lambda. So this is what's called the module. So some of these properties are just to help set up other AWS resources. The actual code, the resources that go along with this, live inside of this folder, API Lambda. And you'll see in there, there's all kinds of, there's a gateway method, method response, an integration response. So just to create one Lambda, you have to basically, it's probably 15 different AWS resources. And so the actual console will auto-generate a lot of these things for you as well. But imagine if you had to go through and click a button to build every one of these things, and then you wanted to stand up a second environment. You had to click and do the exact same thing. So putting it in code makes it so that you can basically apply the formula to any environment. So one way we do that is you specify the code agnostic of account numbers, and then based on whatever AWS credentials you have loaded in, it knows how to go find the Terraform state out in that environment, and then apply the changes. So in general, the way it works is there is a file, it's actually JSON out in S3. You can do it a couple different ways. You can store state a couple different ways, but the way we do it is we put a file out in S3 that defines all the known resources for that environment. Terraform will go download that file, it'll diff it with the definition it has locally, and then it will, anything that it needs to create, it will create, anything it needs to destroy, it'll destroy. And it will only touch things that its state knows about. So it won't go out and if you're in an account that has 500 S3 buckets, and you say take this one away, it'll never touch the ones that are not defined in your state, which is cool as well. Okay, you can pass in environment variables through a pretty simple mechanism. So you have to define them as variables, but then you can actually you just prefix environment variables with a structure like this: tf_var and then the name. And so Terraform knows to grab those and use them appropriately. So things that we usually will define in environment variables, we'll put in like a shell script. So in this case, the only two are the domain name and the broker. Any questions about Terraform?
Where are you running Terraform from?
Either my computer as a developer, or in our CI.
That's why the environment variables come in handy on the CI.
Mm-hmm. Let me see if I have it loaded up.
I've used it on my workstation, but I haven't looked into what's involved in making it run from the CI.
Yeah, the way we usually set it up is we will set the AWS credentials as like secrets in the CI environment, and so they'll auto load, and then we just source this file to get all the specifics. So when deploying to different environments, you just source a different environment file. I could probably run it. just so you guys can see what it looks like. It's kind of, I have one coworker that was not a huge fan of it because it is kind of hard to read as it's going. I just need a credential. And do you know how? Yep. Thank you. Go full screen. So I've wrapped the Terraform in an actual deploy, just so that it automatically applies changes. What you'll see is it's going to go refresh the state. So this is where it's downloading that file from S3. All these lines here are actually all my resources. It's deciding whether it needs to update them. I don't think there's actually going to detect any changes, so it should do nothing. And then if you don't want to just automatically automatically apply them, it will prompt you with a plan that will tell you what it's going to change. So if you're worried about modifying a production environment without a personal review, you can stop it before it actually applies the plan, which is something that we usually will do. Yeah. So it kind of flies by, and you kind of don't ever look at this. At the very end, it'll tell you whether it's succeeded or not. One cool thing I like to use it for is things that are dynamically generated, so like resource IDs. You can actually output them at the end, and then you can grab them for things like getting to the website. So like remembering the website URL or remembering the WebSocket URL. So those are cool. All right, almost done. Almost out of time too, sorry. Okay, so just to show you guys what all of this work did, I have a couple of IoT devices here that are iOS devices. Does anybody want to volunteer? Want to be a user?
Sure.
All right. You're getting the test 2 device.
All right.
So I'm going to go ahead and connect you to the broker. You should be good. Anybody want test 3? Could you help me out?
Oh.
Just gotta type in that box and hit send. All right, so I have the site out here. This is my web app that's actually listening for new messages. So if you guys want to type in a message and hit send, it should pop up here. I also have an iOS simulator.
Should I connect first?
I think you're already connected. If the send button is blue, then you should be connected. And so these devices are all talking across MQTT. So they are actually not interacting through WebSockets, through any of the AWS infrastructure that I just showed you. They're talking directly to each other on an MQTT topic. So they are all posting messages to the topic, and they're all subscribed to the topic. So any messages that show up on the topic will show up on the device. The cool thing is, though, the web is using all of that AWS infrastructure that is basically collecting those messages and is also showing it to the user, as well as also lets the user interject their opinion. So the web can actually send messages as well. It's going to take a little bit longer because of that Lambda cold start, but you'll actually see those messages on the devices as well.
So then with the MQTT, is there the Lambda cold start that you still have to do because you have a Lambda injection, Lambda piece between that, or?
So the MQTT is not requiring, it's not hitting the Lambda to do the MQTT messages. That's going straight through the MQTT broker. What I'm doing though is I'm grabbing those messages off the broker in AWS so that I can get them in my Dynamo database and get them to the web. And so, let me pull this back up, just the diagram. So the devices are only interacting with this part of the architecture. Occasionally, so if I send one from the web app, it'll send it all the way back through here, through the API gateway, through Dynamo. Actually, no, I think it goes through here, into Dynamo, as well as writes to IoT Core. So the web app uses all this infrastructure, but the devices are only on MQTT.
And the ingestion Lambda, what part does that do?
So once the actual device sends a message, that will trigger this Lambda to write it to Dynamo.
Okay.
Yeah. So think of it as all of this stuff is to watch the critical data that somebody in an office somewhere has to actually see in real time. So we actually had a requirement that said this whole pass has to take less than 15 seconds. And it could be across the world. So all of this technology scales across regions. I think we couldn't do it in Russia, we could do it in China. But other than like Russia and China, everywhere in the world was covered by high availability of this infrastructure.
Is the infrastructure still available from those countries, just not hosted in those countries, or do you see that it's actually actively blocked?
So China, I believe, is actively blocked. Like, I don't think they have any data centers in China.
Okay.
And so this is all where AWS is. So I
Right.
think,
No, that makes sense.
in general, AWS is blacked out of China.
Right.
Russia, I think there might be data centers, but the actual country has like some weird things that make it really, really difficult to secure your data going out of it. So,
Okay.
so this doesn't solve those problems. But with those, you're probably looking at custom country collaborations where they open up something specially for you. Yeah.
You said that a requirement was getting a message over in less than 15 seconds. I was wondering what the upper end of that actual delay was.
So 15 seconds was how long that was our space to actually move on this. I think the worst we did was, I think we had some data when we had really bad cold starts, taking 7 seconds. So, and that's because cold start, and then this thing was pulling every 5 seconds. So like we did iterative development, so we did some really bad things early on. We didn't do like the pub sub. So this would only check every 5 seconds. So 5 of those 7 seconds was this thing waiting 5 seconds. So as you guys can see, like, I mean, somebody wants to send a message real fast, or I can do it, and I guess in front of you. It looks instantaneous. Like, it's amazing that all this infrastructure actually just did something. It's like this one will go almost immediately. I guess it's a little bit more compelling if you do it from a device. And so it's going through like 5 different managed services just to get to the web browser, but it's super quick. Yeah, I would not suggest building a chat app this way. This was totally for demonstration purposes. I would suggest using MQTT for chat. That's really cool. If you want a cheap or an easy way to set up a broker, IoT Core is great for that. But yeah, this is a highly convoluted chat app, so I would not suggest all the AWS infrastructure was highly unnecessary for this.
Any other questions?
All right.
We'll wrap it up.
Awesome. Thanks, guys.
If you do think of any questions, feel free to stick around and chat with Ben. Ben, can you stick around for a little bit?
Yeah.